Tonight's speaker is Dr. David Morrison. Dr. Morrison is a senior scientist at the NASA Astrobiology Institute at the NASA Ames Research Center in Moffett Field, California, where he participates in a variety of research programs in astrobiology, the study of the living universe. Those of you who take astronomy here at Foothill College will also recognize his name as the author of your textbook. Dr. Morrison obtained his doctorate in astronomy from Harvard University. He's the author of more than 150 technical papers and a number of popular books on astronomy. He's been a science investigator on the Mariner, Voyager, and Galileo space missions, and he's received several medals from NASA for his work. In particular, a NASA medal for protecting the Earth from asteroids, which is his topic tonight. He is also a recent recipient of the Sagan Medal of the Division for Planetary Sciences of the American Astronomical Society. This medal is the highest honor given to a planetary scientist for popularizing astronomy. And you will see him wearing his medal tonight because, in fact, this is one of the talks that he's giving in honor of receiving that medal. Now, I know Dr. Morrison as a friend and a colleague, but the world, I think, knows him best as a distinguished scientist with a special knack for explaining science with authority, clarity, and flair. I think you'll see that in evidence tonight as he discusses Taking a Hit, Asteroid Impacts and Evolution. Ladies and gentlemen, it's a professional honor and a personal pleasure to introduce Dr. David Morrison.
Hello, everybody. It's a pleasure to be here, and I am so glad to see so many of you. You must have heard that I am not going to live up tonight to my sometime reputation as Dr. Doom. When I first started talking about the hazard of asteroid impacts nearly 20 years ago, I got that name because I was pointing out a hazard as if we needed another hazard, one that we didn't know about. Now I'm going to talk about, in fact, how we're dealing with that hazard with considerable success. In fact, in the 16 or 17 years I've been on this job, not one person has been killed by an asteroid. So it's my most successful activity. Well, what we're going to do is actually combine two things here, astrobiology and asteroid impacts. And that's not so hard to do because astrobiology is about the relationship between the cosmos and life. And one of the things that first drew our attention to impacts was the discovery that it was an asteroid impact that produced the mass extinction at the end of the Cretaceous period, did in the dinosaurs, had a profound change on the history of life on Earth. In fact, I can hardly think of a more direct way, other than sunlight, that the cosmos comes home and can affect the history of life on Earth. Let me start, though, just by reminding you that even though you haven't read about any recent major impacts, it does happen. We are coming up now on the 100th anniversary of the impact in Russia, in the Tunguska region of Siberia, which happened in June 1908, leveled about 2,000 square kilometers of forest, and has been estimated as the equivalent of a large 10 to 15 megaton city killer kind of explosion that was due to an asteroid, a fragment of an asteroid, if you will, roughly the size of this building, that came in over Siberia, exploded before it hit the ground, did all this damage, and first called humanity's attention to the fact that things could come hit us, that the sky could fall. It's still a weird thing, Tunguska. It's way out in the wilderness of Siberia. The original blast probably didn't kill anybody, and I think if it happened at the same place again, it still wouldn't kill anybody because it's really way out there. The new capitalist Russia is making some use of it. This is straight from a website in which it talks about Tunguska blast as a powerful dietary supplement, which originates from the meteoritical events in 1908 in Tunguska, and that it created an oasis of fertility where herbs and plants grow and so forth. So if you want to, you can go on the web and look for Tunguska and find this place and order some of their wonderful dietary supplements. I don't recommend it, but you can. Well, the connection between impacts and extinctions is rather more profound, because a mass extinction is just about the worst thing that can happen to us here on Earth. A mass extinction is defined as an event in which more than 50% of all species go extinct. Not 50% of living things are killed, but 50% of species go extinct, which means there's not a single survivor of that species. We may have had such events through much of Earth history, but the fossil record only really tells us about the last 560 million years. And in that period, there have been at least 5 big mass extinctions. What you see here, and I apologize for the fact that it's not very clear, but here are 2 ways of showing the data where people look at the fossils from the last 500 million years and estimate the number of species or families or genus. And in the first one, you see the number as a function of time. And this is only big creatures, at least the size of bugs. It doesn't count the microbes and the little things that don't leave fossils. And you can see it has ups and downs. And each one of these downs is a precipitous drop in the diversity of life. And this is just the other way around. This shows the rate of change. So each drop up there corresponds to a peak here when there is a very concentrated period of mass dying. And for a long time, it's been a real mystery as to what could produce that. There's obviously a background level of extinction and of new species being formed. But the idea of something catastrophic, and I do want to emphasize the catastrophic. No one knows in most cases how long it took for the extinction to take place, but I think you have to think in terms of years, not millions of years. Because if something changes gradually, sea level change, global warming, whatever, most species will adapt one way or another. To actually kill off more than half the species on Earth, it has to happen very quickly. So we're looking for events that are catastrophic. And the largest was the one 251 million years ago up here, when more than 90% of all species went extinct. And the most recent, and the one we certainly know the most about, is 65 million years ago at the end of the Cretaceous. That's this peak right here, which has always caught our imagination because it corresponds to the end of the dinosaurs. Well, this is a story that I'm sure most of you know at some level, so I will go through it rather quickly. But the discovery that the end Cretaceous mass extinction was due to an impact of an asteroid or comet is one of those revolutionary scientific discoveries. It suddenly gave us a whole different perspective on the dynamics of evolution. And part of what makes it so neat is it was all done in one paper. There's one paper published in 1980 in Science by the father and son, Louis and Walter Alvarez, and their co-investigators, who are shown in the lower right, in which they didn't just discover and publish the data. They wrapped the whole story up. And very briefly, this is it. You have a cross-section here. This one is from Gubbio, Italy. But any place that you have marine sediment, that is sediments formed in the ocean, you can build up this, and it's just this time sequence. The lower things are older, the upper are more recent, and this is just one little bit of a huge cross-section that goes on for hundreds of meters or even kilometers. Why marine? Because that's just the way erosion works. Hardly anything is left on land because the land is constantly being washed into the sea. So the sediment builds up in the sea, and there you have the record. Now, what is interesting, of course, is what this material is. It's limestone. It's made of the fossils of little microscopic sea creatures. Incredible numbers. I mean, most of the material here is these little fossils. These little shells can be identified, and you can look at the population down below this boundary, and there's thousands of different species. And then you look above the boundary, and only 10% of those species made it through whatever happened here. This point of difference, and you can see it's just about the width of your finger. Something dramatic happened then that caused a 90% change in the species of these marine creatures. And there's no question about where it happened because, there are plenty of fossils. You just can look at a little thimbleful here and compare here, and you can see the difference. What these gentlemen and their team discovered was that there was the extraterrestrial metal iridium in this layer, and later a lot of other things as well. How many of you have a platinum ring? Platinum is valuable, right? Platinum and iridium are very closely related. They are valuable, not because they are scarce in a cosmic sense, but because almost all, 99+% of it on Earth, went into the core when the Earth differentiated. And so that's where it's found. It's extremely rare on the surface, and yet it's enriched more than a factor of 100 in this layer. There are other things in this layer that indicate something happened. There's a lot of shocked quartz that shows an explosion. There's lots of soot, which indicates a global burning. And the whole story that they pulled together was if an asteroid hit, and they could estimate the size of the asteroid from the amount of iridium, if an asteroid 15 kilometers in diameter struck, it could produce all of these effects. It could produce a global firestorm because the material that was excavated from the crater would go up thousands of kilometers and fall back down and give up its energy into the atmosphere. It could produce a collapse of photosynthesis from the black dust that would be in the atmosphere for years. And it was much more than a very bad day. It was truly a global catastrophe in which we can imagine, in terms of individuals, far more than 99% died. And only relatively few were able to survive. And that story is told in this little half-inch thick layer, which is found not only in Gubbio, but everywhere on Earth where this area is preserved. Well, we're pretty sure we know what happened, especially once the crater was found. The largest known impact crater on Earth, called Chicxulub, which is in the Yucatan, and is buried under a couple of thousand feet of sediment, so it's not exactly obvious on the surface. But one impact with 15 kilometers diameter could produce atmospheric heating, producing a global firestorm, followed by cold and an insult, if you will, to the life on Earth that it took a while to come to regain. And the dinosaurs didn't make it at all. Not one single dinosaur survived after that. Our ancestors, the mammals, didn't do too well. Half of their species went out. Awful lot of things went extinct. So the evolution changed its direction because of this random external event which had nothing to do with the normal course of evolutionary events. It provides us a new perspective on natural selection. I'm not going to try to go this in detail, but just to give you the basic idea. The classical Darwinian view is a uniformitarian view in which the environment changes gradually and creatures adapt through natural selection to the changing environment and to competition. And this is what we all learned in grade school. The dinosaur that could run faster would catch the one that couldn't run so fast, or the giraffe with a long neck could reach and get leaves that something else couldn't, and you would have all of this constant adaptation to be a little faster, a little stronger, a little smarter, or whatever it was. And that's the normal dynamic of evolution. Now we introduce something completely from left field, where there suddenly is an external catastrophe not predicted, nothing is adapted for it, and the rules are changed. Now it doesn't help to be smarter or bigger or run faster. In fact, on the case of land animals, the ones that survived were the little creatures that could dig a hole and hibernate until the bad times were over, or things like crocodiles in swamps that could dig down into the mud, or plants that produced fire-resistant seeds so that they could just lie fallow for several years and then come back. And so you have a whole different pace of evolution that occasionally interrupts the normal uniformitarian ones. And the genes that allow you to survive the catastrophe are not necessarily the ones that have been selected for in the tens of millions of years between catastrophes. So it's a kind of strange thing that comes about, that we are here, for instance, because our ancestors were able to survive that impact. The dinosaurs are not here because they couldn't. And when we talk about catastrophes, of course, there's nothing much more sudden than running into an asteroid. And in the case of the dinosaurs, which are land animals, and many of them quite large, I think it's pretty clear what killed most all of them, and that was this firestorm from the ejecta falling back, which happens about 20 minutes after the impact. So somebody asks you, how long did it take the dinosaurs to go extinct, and are expecting you to say, well, 1 million years or 500,000. The right answer is about 20 minutes. And a lot of other things went extinct, too. So we have a different dynamic here to study. And it can still happen. There's nothing about the Cretaceous impact 65 billion years ago that is any different from now. Remember, that was less than 2% of the age of the Earth looking backward in time. This was not some ancient period of heavy impacts. And we occasionally have reminders of this today. Have you all heard or read something about the Peruvian impact last month? No? I've wondered how much it was actually being in the newspapers. It probably not. Probably the reason you haven't seen much is it's such a gosh awful place the television crews haven't gotten there yet. It's on the shores of Lake Titicaca at about 12,000 to 13,000 feet in Peru. In fact, it's right on the Peru-Bolivian border. And the information that is filtered out is very unclear. And for a while, most of us were really quite skeptical that it was a real impact at all. But there is this crater, which is about 12 meters in diameter and several meters deep, filled with water. You can see it's right on the edge of this lake. And the one thing that makes you think this really might be real is that some scientists from Lima went up and collected fragments like this, which really do appear to be meteoritic. They appear to be from space. They have not dug down to find whatever the central object was. And the latest story I heard today was that they're saying the crater itself is unlikely to last more than 2 or 3 months because it's basically on the edge of a lake. And the mud is just going to flow in and it's going to be a mess. So they're going to have to go up there and figure out what really happened. From the point of view of those of us who study impacts, it's really very strange. Because the thing I want to emphasize about the hazard of impacts, which we'll be coming to, is that they hurt you really only if the cosmic body strikes the Earth at cosmic velocity, which is like 20 kilometers per second. Not as fast as a speeding bullet, much, much more than that. And the alternative of just being hit by a meteorite, a rock from space, is really not anything you have to worry about. In the case of a meteorite, if it hits you on the head, you die. But if it lands 6 feet away, all it does is splatter dirt on you. Because they just aren't going that fast. It's like a stone dropped from an airplane. In the case of something that still has its cosmic velocity, when it hits, it explodes, in effect, and produces a huge crater and all kinds of damage. And the atmosphere generally protects us from those. Well, it looks like something strange went on here. I do not think from the appearance of that crater that this thing came in at cosmic velocity. It looks more like just a rock dropped from an airplane, although I'm not seriously suggesting that what happened. I don't know how a rock that size would get through the atmosphere. I'm still skeptical, but at least it does help show us that things are happening that we don't necessarily understand, and this one is another one. This week, a paper was published in the publications of the National Academy of Sciences with a whole mess of authors indicating evidence for an impact that took place just 12,900 years ago. Not 65 million, like the dinosaur killing one, but a mere blink of the cosmic clock. And they think this may have been the cause of the extinction of the megafauna in North America, like mastodons and mammoths. And I don't know if that's credible or not, because again, their suggestion that this was some kind of comet shower, not a single impact, but a whole bunch of impacts, none of which produced a crater, seems to be calling on a kind of object out there that we've never seen. I hate to be presenting such inconclusive stuff, but I just wanted to show you that there are things out there right now that we do not understand. And I'll give you the whole rest of the talk as though I know exactly what I'm talking about. But remember, I don't. Well, how do we go from these past events to current? I've told you that if impacts happen in the past, they can happen in the future. And indeed, you can get a very good perspective on how frequent impacts are, not by looking at the Earth, but the Moon. You've all seen the Moon through a telescope or pictures. There are 30,000 impact craters on the near side of the Moon that can be seen with even a small telescope. And the Earth and the Moon have lived together for 4.6 billion years. So the Earth would be just as heavily cratered as the Moon if we didn't have geological and erosive forces to erase the craters. We have been hit over and over and over. And that will continue in the future. It's not something limited to the past. When some of us began to point this out in the 1980s, we were largely influenced by that impact 65 million years ago. I mean, that, as I say, was revolutionary. That changed our perspective and made us realize these things could happen today. And even an impact that is minor on the scale of the planet can do an awful lot of damage. That end Cretaceous impact, I said, was a 15-kilometer diameter object. That is less than 1/10 billionth of the mass of the Earth. An impact like that has no effect on the Earth. It doesn't change our orbit, our spin, our magnetic field. To the Earth, it's just a pinprick. And yet it was enough to produce a mass killing. And so we suddenly became sensitive to this idea and went through the thought experiment to see if this was a contemporary hazard. And I talked to the Congress about it. And I think this, from 1991, is a very good statement of the problem. And what the committee said is the chances of the Earth being struck by a large asteroid are extremely small, but because the consequences of such a collision are extremely large, the committee believes it's only prudent to assess the nature of the threat and begin to deal with it. And that's what they asked NASA to do, and I had the good fortune to chair the committee that studied the nature of the hazard and what we could do about it. Just to show you the kind of objects we're dealing with, this is the largest of the near-Earth asteroids. It's about 30 kilometers long, so it's as big as almost from here to San Francisco as that end of the part of the bay. And it's irregular and heavily cratered and rocky. And certainly an interesting object, but don't think of these as round bullets. They aren't. This Eros we've studied in great detail. A NASA spacecraft went there, orbited it for a year, and then landed. At the other extreme, the small objects, this one is about as big as just the central part of this campus. And it was visited 2 years ago by a Japanese spacecraft. Hayabusa, and it's called Itakawa. I think there's some more than a coincidence here that the Japanese chose to go to an asteroid named after a Japanese scientist. But it's much smaller, and if you think about it and compare to that last one with craters, you'll notice there's no craters here. It's only lumps. Some very different process. These are the size objects that are by far the most likely to hit us. There are many, many more small ones than large ones. Eros is bigger than the asteroid that did in the dinosaurs. Fortunately, it's not scheduled to hit the Earth anytime soon, if ever. But a little one like this can come along anytime. And don't kid yourself that there are a bunch of astronomers out there staring at the sky waiting to see one coming. Without the kind of survey, which I'll discuss in a minute, the average warning that you will have of an incoming asteroid is about 5 seconds. The first you'll know is when the sky lights up and then the ground shakes. There won't be anybody seeing it on the way in. Well, one way to look at this is to estimate the frequency of impacts and get some idea from that about what we should or shouldn't worry about. And this is my only graph. Stick with me for a minute. I want you to be able to read it, but then we won't have to look at it anymore. What I plotted here are the size of the impact. And now this isn't the diameter of the asteroid. This is the energy. And for energy, I've used megatons, the unit we all are familiar with in talking about nuclear explosions. The Hiroshima nuclear blast was down here. The biggest ever done, the Russian one, was here at about 65 megatons, and then it goes on up from there. On this side is the average interval between impacts that size. And very conveniently, that almost lies on a perfect straight line. The end Cretaceous, and I apologize, we don't normally spell Cretaceous with a K, but the Germans do, and that's why it's called the KT, the Cretaceous Tertiary. It is 100 million megatons, 100 million tons of TNT. The Tunguska that I told you about at the beginning is about 15 megatons. And you can look at the frequency. The KT is going to happen about once every 100 million years on average. A Tunguska once every 1,000 years on average. And so you can predict, in a sense, what the statistical risk is. If these just come randomly in time and you can't predict it, then you can ask, well, what is the chance that it will happen this year? Or you can even estimate how many people will die in each one of these. And I could look at Edna and say, what is the chance that it will say on your tombstone that you died from an asteroid? It's more than zero, unless you're planning to get your tombstone carved today, because there's no warning, remember? When Clark Chapman and I first put this together, it was interesting because we carried the curve up and looked at how often there should be a blast the size of the Hiroshima atom bomb. And you can read from there, it's about once a year. And we had one of those moments in science when you think you've really screwed up. And you think, well, maybe I made some huge arithmetic error. Because we said to ourselves, if there were something as big as the Hiroshima atom bomb going off on Earth every year, wouldn't we have heard about it? Wouldn't we read about it in the papers? How could this be hidden? And then we did some more calculations and realized that things that size explode as soon as they hit the atmosphere, 50, 60, 70 kilometers up. And the shock wave never reaches the ground. But how could we verify that? Well, we were fortunate. We did this work in about 1991 and 2, at the end of the Cold War, when the Air Force and the agencies that deal with national security were getting a little more open. And we realized that there were large numbers of down-looking satellites, surveillance satellites, using infrared and visible, looking at the Earth, that ought to see the flash of light when one of these impacts takes place. And we got to go down to what was then Falcon Air Force Base, now Schriever Air Force Base, the head of the Space Command, and talk to the people. And they said, sure, we know about those. We asked them, have you received any big flashes? They said, yeah. We said, do you know what they are? Sure, they're meteors. And they said, we've known that for 25 years, and we built our software to exclude those because we know they're not enemy weapons, and so they don't bother us, and we don't even keep very good records of it. But there were enough records, and now there are better, to verify that that is exactly right on the curve, that there is something as big as Hiroshima about every 6 months. And these days, the Air Force puts out a press release once or twice a year telling about those. Well, as I said, I can calculate the statistics. That, by the way, came out very shortly after Katrina and the FEMA activities. I could calculate probabilities. I could calculate frequency of impacts. I could calculate where the risk lies. I can tell you, for instance, that you're more at risk from an asteroid 2 kilometers across than from one that's either larger or smaller. But in fact, that is not what most people want to know. They are not really interested in the probabilities, which are low. They want us, the scientists, to tell them when and where the next impact will take place, to discover the object before it hits. And so that's what we're going to do in the rest of this talk. Not deal with statistics and small probabilities, but find out if we can find the next impactor before it finds us. And we call this the Spaceguard Survey. If we look with a survey and find these objects one at a time and calculate their orbits, then we can provide decades of warning. Of course, if we don't look, we'll be just like the dinosaurs. So the first step is an astronomy step. It's to have telescopes and look for these objects so we can find the next one before it hits. And let me just say, there's an analogy I think that's useful when you talk about the shift in perspective from statistics to actually searching for them. If you are foolish enough to try to jaywalk across El Camino, for instance, I doubt very much if you ask yourselves, what are the statistics on pedestrians being hit crossing this street? I bet instead you look to see if there's a car or truck coming. And that's what I'm saying we should do with asteroids. Let's look and see if one is coming. The Spaceguard Survey began operations 10 years ago, 1998, and it's based on relatively small telescopes, just 1 meter in aperture, but with very sophisticated detectors and computers. In fact, the computing power to support the Spaceguard Survey didn't exist before the mid-1990s. The goal, which has been established by NASA, is to find 90% of the near-Earth asteroids larger than 1 kilometer diameter by the end of 2008, which is within 10 years of the start. And 4 telescopes have done most of the searching. It's a completely open operation. Every clear night they're observing, and they process the data within 6 hours, and by 3 o'clock the next afternoon they're posted on the internet. And so you can look and see each day how many asteroids are observed, how many are discovered, what their orbits are, and make your own conclusions if you want. But of course, part of the process is to filter through these data and find out which orbits correspond to objects that could hit us. Let me say one thing very clearly. Only in Hollywood do asteroids change their orbits capriciously. It's a wonderful plot thing that a comet or asteroid suddenly gets knocked out of orbit and heads for Earth. But in fact, it is a very deterministic thing. Newton's laws really do work. The same thing that lets us send a spacecraft to Neptune will let us predict an asteroid impact decades or centuries in advance once we find it. So we don't worry about anything changing. We just want to do this survey and see what's out there. I mentioned this, maybe I'm being defensive, but we constantly get questions raised, things I call myths, about the survey. They say, oh, but your telescopes don't work at daytime, they only observe at night, so aren't you going to miss half the sky? They say, but your telescopes are only in the northern hemisphere, so you're not looking at the asteroids in the southern hemisphere. The point, of course, is that these asteroids that are going to hit us will come by the Earth thousands of times before they hit. And if we miss them this year, we'll get them next year. We just want to have a maximum throughput on the system. Another thing very strange, I guess people don't look at the sky very often. They say, but a ground-based telescope can't look at something in the direction of the sun, something in an orbit inside the orbit of the Earth. How many of you have ever seen Venus? Bright against a dark sky. Venus has an orbit way inside the orbit of the Earth, only 7/10 of the distance from the sun than we are. We can see it just fine. In fact, we can see it better with ground-based telescopes than space telescopes. The Hubble can't really look that close to the sun. So the bottom line is it really doesn't matter whether you look from one site or many, northern hemisphere or southern. You just want to maximize the throughput of the system. What you're doing is photographing a patch of sky, doing it again 30 minutes later, again 30 minutes after that, looking for the faint moving asteroid against the tens or hundreds of thousands of fixed stars. And given time, you'll find them all. If you don't get them on this pass, you'll get them on another. You probably know the story. I think it's always amusing to talk about throughput. When the Berlin airlift started and we were desperately trying to fly enough food and coal and goods into Berlin, the planes just took off one after another and flew into the airport in Berlin. And, of course, sometimes the plane will miss its landing. There'll be a little fog or it will not come in right. And any pilot would say, of course, if you miss, you'll come around and do it again and land the second time. But that stopped the whole string of planes coming along behind. So they adopted the rule, if a plane misses its landing, it turns right around and flies all the way back to West Germany and gets in line again. Because you want to maximize the throughput. And that means you give up individual things. If we see an asteroid and lose it, we don't worry about it. We don't divert the telescopes into looking for the lost asteroid. We go ahead and try to get the system to work. And it is working. Here is the record of discoveries. These are total. We now know almost 5,000 of these near-Earth asteroids, the ones that could hit us. And of the big ones, more than a kilometer, we're coming up there. But can you see that the curve rolls over? We aren't discovering them as fast as we used to. Why is that? Have the astronomers become lazy? Do the telescopes not work as well? No, the point is this is discovery. You can only discover an object once, and then it's in the catalog. What the telescopes are doing now is rediscovery. The majority of the asteroids found every night by this automated system are just rediscovery of those we've already had for the big ones. And that just proves the system is working. In fact, as we get nearer and nearer to completeness, we'll find out we're less and less efficient. If we want to change from this size asteroid to the much, much more numerous small ones, then we have to go to bigger telescopes. That's what I call the Spaceguard Deep Survey. You don't just build more little ones. You take a whole big jump into what is called the Large Synoptic Survey Telescope, which is a horrible name, and I hope pretty soon they'll name it after Newton or somebody, and so we can call it something better. But this has been recommended by the National Academy of Sciences. It's going to be built in the next 5 years in Chile, and it's going to be the astronomer's dream telescope for throughput. Wide angle, deep observing. It can observe the entire sky down to something like 25th magnitude in 2 weeks and do it over and over and over. It will give us Universe the movie. And it'll be available, we hope, on your home computer. So you could pick a little patch of sky you liked and watch it over and over and see what things were happening, what was changing, what was variable, whether there was a gamma ray burst, and in the process, pick up these asteroids. Well, Congress is supporting that. And at the end of 2005, they did two things. They not only asked NASA to look into working with such new telescopes to go to much smaller impactors, they even changed the basic legislative charter of NASA to give it responsibility to resolve any ambiguity about what agency was supposed to be in charge of dealing with asteroids. So they asked for another study, which I did not chair. It was done at NASA headquarters and was just released a few months ago. Actually, it wasn't released. It had to be take a Freedom of Information Act request to get it out. And it talked about a lot of things that one could do. It had 271 pages, but in the end, the response to the Congress was that NASA doesn't have the funds to carry out this survey. And some members of the House of Representatives weren't too pleased by that. And the fact is that next week is a hearing in Washington to examine the NASA report and what it means. Let me now conclude by talking about planetary defense. We don't do this just because it's fun, although it is, to find these asteroids. We do it because if you find the asteroid with decades of warning, you can do something about it. It is the only natural hazard that we normally deal with for which that is true. Here we sit. How many miles from the San Andreas Fault are we here? Not very many. And we know those two tectonic plates are continuously moving with respect to each other. You can use GPS to do it. There are lots of ways. The Pacific and North American plates are moving along at about the same rate at which your fingernails grow. And eventually they will give in a big earthquake. There's simply no way that could not happen. I can't imagine you could ever stop a volcano from erupting. But if you discover an asteroid on a collision course with Earth, it can be, at least in principle, it can be deflected. You need lots of warning. And then you send a spacecraft out and change its orbit ever so slightly. You either speed it up or slow it down. So when the time many years later arrives that the spacecraft and the Earth would have hit, the spacecraft is either 6 minutes early or 6 minutes late and misses the Earth. And this is a practical thing in principle, although we don't know exactly how to do it. It only makes sense if you have decades of warning. If we found one by a fluke with a month warning, well, drink your best bottles of wine, because there's nothing anybody can do about it. There is one asteroid that's been particularly interesting called Apophis. When it was first discovered, while the orbits were still quite uncertain, by just an amazing fluke, it turned out that the formal errors were such that it had an estimated 2% chance of impact on Friday, April 13th, 2029. And this was by far the biggest red flag that's ever been raised in this survey. And we discovered that on the 24th of December of 2004. The orbit was calculated to show this high probability on the 25th of December 2004. And it probably would have hit the newspapers on the 26th of December 2004, except you may remember something else happened then. The earthquake and tsunami completely dominated the news, and properly so. 250,000 people killed. And by the time that got off the front page, a week later, we had recalculated the orbit, we had new data, and it turned out you never heard about this. But when something gets to be that kind of probability, you can do an interesting thing. You don't know whether it will hit, but you can say if it hits, we know it will be along this line, which is basically the projection of the orbit of the asteroid onto the map of the Earth. So when we thought there was a 2% chance, Rusty Schweikart in particular went through the first one of these calculations and said, the whole Earth isn't at risk. It's just along this line. And then you look at where that line goes. Crosses London, very close to Paris. It crosses northern Iran, Afghanistan, India, and so forth. Now, let us suppose that one had the technology to change the orbit a little bit, and you were going to move its point of impact. Think about the political implications once you're talking about a particular object. Would you be more worried about a hit on London or a hit on Afghanistan? And who makes those kind of decisions? Well, one of the biggest proponents of planetary defense was Edward Teller, the father of the hydrogen bomb, who lived just a few miles from here during the last couple of decades of his life. And he became a strong advocate of using nuclear explosives to deflect asteroids. People have speculated about why he felt this way. Clearly, as the father of the hydrogen bomb, he kept hoping that his bomb could be of some use other than annihilating people. And I think he really thought that this was an opportunity to develop a new generation of bombs, not to attack other people on Earth, but to attack asteroids. And I was with him in 1994 when he made his first visit to the atomic city of Shnezinsk in Russia, in the Urals, the equivalent of Lawrence Livermore Laboratory. And we saw the world's largest bomb. I mean, it's a mock-up of it in their museum. It's supposed to have been good for 100 megatons. It was actually fired at, I think, 60 megatons. And Teller blithely said, we can make one 100 times bigger than that. Let's go out and do it in case we have to protect against an asteroid. Not everyone agrees with that. And one of the big questions has been what actually should be the approach you would take to defense. There are a number of technical suggestions. One of them is indeed to use a nuclear bomb, although it's not one that's very well understood, because while we know what happens with a nuclear explosion on Earth, a nuclear explosion in space is very different. There's no fireball and shock wave to move the asteroid the same way it would be on the ground. And Teller recognized that, and his position was that science has to do with experiments, and so what we should really push for is an experiment to nuke a poor innocent asteroid and see what happens. Not necessarily a bad idea. Most of us think, well, we can wait. We don't have to develop an asteroid defense because the Spaceguard type survey will give us decades of warning. And so why spend the money now when we don't know what we're going to have to defend against? We don't know when we'll have to defend. But the question is, well, should we be doing some preliminary work now? Everybody seems to agree we should carry out the survey. But the idea of beginning to take the next step so that we could do something if we found one headed for the Earth is more problematic. And it's a matter of money. How much should we spend on the defense of the planet? It's a matter of responsibility. Is this an international effort? Is it something for the U.S. to do? We're the world's only superpower. We seem to think we can police the rest of the world in various other ways. Maybe we should also develop an asteroid defense. But then, can you trust the U.S. or anybody else to do that? Since this lecture is part of my Sagan Medal thing, I want to conclude by talking about Carl Sagan's position on this, because he, like Teller, became very interested in the last years in his life in the question of protecting against asteroids. It's a very real danger. It just doesn't happen very often. And he was concerned about the risk, but he was also concerned about the hazard inherent in developing a defense system. He even pointed out, for instance, that if you had the technology to take a dangerous asteroid and deflect it away from the Earth, you had the technology to take an asteroid that would have missed us and deflect it into the Earth. And what was the risk of that? He called this the deflection dilemma. If you develop the technology to do a good thing, you may end up having an unintended consequence that's even worse than what you were doing. And he typically had a good imaginative way to illustrate this by telling a story, a true story, called The Marsh of Camarina, about the Greek city-state in about 500 BC in Sicily, which was Magna Graecia then. And this is, I'm told, a completely true story as far as we can trust the history back that far. They had a health problem. And I don't know if it was malaria or what, but the city fathers figured out that the swamps around the city were probably the cause of the problem. So as a public health major, to make their citizens more healthy, they drained the swamps. The enemies around them, as soon as the swamps were gone, realized the city was undefended, attacked, burned it to the ground, killed all the men, and put the women and children into slavery. And there's been nothing left ever since. So this is Sagan's parable about unintended consequences, that doing a good thing, trying to improve people's health, could ultimately have a much worse consequence. Sagan, however, in the end, I think, had the right perspective, because he said, if we look at this from a long-term perspective, if we think about not just this decade or this century or this millennium, but if we talk about human civilization surviving for hundreds of thousands or millions of years in the future, then asteroid impacts are the biggest risk. They are the biggest known natural hazard. Very rare, but they could end civilization. They could even produce the extinction of humanity. It happened to dinosaurs. It could happen to us. So he said, while we have the short-term political problems of how we would deal with a defense system, who would build it, who could be trusted to control it, on the long term, we are going to have to deal with this problem. So let me just read this from his book, Pale Blue Dot. Since hazards from asteroids and comets must apply to inhabited planets all over the galaxy, if there are such, then intelligent beings everywhere will have to unify their home worlds politically, leave their planets, and move small nearby worlds around. Their eventual choice, as ours, is spaceflight or extinction. Let me now give you a quiz. I really am curious, because I've explained how impacts are part of the natural process of evolution. If it had not been for the impact 65 million years ago, we would not be here. Or maybe we could be, something like this, but the building would be shaped differently and the seats would be much larger, because you and I would all be dinosaurs, intelligent dinosaurs. The dinosaurs were doing just great up until that impact. They were not in decline. They ruled the world. They'd ruled the world for 100 million years. And yet, in a moment, they were wiped out by an impact. And if it hadn't been for that, we wouldn't be here. It's a really important part of the evolutionary history of the Earth. Now, I'm telling you, and Carl Sagan was advocating, that we might want to get the technology to stop this from happening again, to interfere with the natural process of evolution. So I want to see a show of hands. How many think that is morally and ethically acceptable for us to interfere in one of the most fundamental aspects of evolution so that it won't happen again? Show of hands. All right. Now, not everybody put their hand up, so maybe there are some others. How many think it is morally and ethically questionable for us to defend ourselves against an asteroid that could cause an extinction? A few. I should talk to you guys later. In fact, there are more here who think it's ethically unacceptable than is usual when I give these lectures. I'm with Sagan. I think humanity is worth saving. And I think that, in fact, we are not outside of the process of evolution. We are a part of evolution. If evolution has produced a being smart enough to recognize the danger, to carry out a survey, to build a spacecraft that could deflect an asteroid, then that is not contrary to evolution. That is, in fact, just an extension of this process. But I recognize that there is a legitimate difference of opinion on that. I will give you that as something to think about when you go home. And think about also the fact that the astronomers who for the last 10 years have been carrying out this survey have, in a sense, been making you safer. 3/4 of the asteroids that pose the greatest risk have now been discovered, cataloged, their orbits calculated, and have been shown that they will not hit. So the chances of you being hit by an unknown asteroid in that size range today, that is, of the Earth being hit, is only about 1/4 what it was a decade ago. So in this sense, astronomers are saving the world. Thank you. And I would, of course, be delighted to answer questions.
Thank you, David. Thank you so much, Dr. Morrison. A terrific lecture. And we do, as you heard, have the opportunity to ask some brief and to-the-point questions. There are 2 microphones set up in the middle of the auditorium. You see that there's a space between the upper section and the lower section. What we ask, if you have a question, is that you line up in front of the microphones. And I'm going to ask Dr. Morrison to take turns, one microphone to the other. If you're not able to stay, we are very glad you were able to come. Take the sheets on your way out, and we hope to see you November 14th. But for most of you, I'm now delighted to invite Dr. Morrison to take questions.
I can't see very well.
Either of us.
Right there. Start with you.
Is this on? This on? I wonder if you have considered the possibility of larger asteroids that are not near the Earth, maybe with more eccentric orbits.
Yeah, they're called comets. And I very carefully did not talk about comets Fortunately, asteroids constitute most of the risk, something between 95 and 99%. But none of this works for comets. A survey would not pick up a comet decades in advance because they come in from deep space. We could not calculate a comet's orbit precisely enough to know if it would hit or not. We wouldn't know whether to try to deflect it because we might just as well deflect it into the Earth as away from the Earth. And it is definitely not within current technology. So if you want to worry tonight, worry about comets. Maybe our grandchildren can solve that problem. I'm only dealing with asteroids, and I know we're never going to find the last asteroid either. This is a risk reduction program, but there's no free lunch. There is no way to absolutely make the Earth safe from impacts.
Yes, thank you. I was under the impression that the extinction at the KT boundary took about 1 million years, as you mentioned, but you're also saying that the extinctions took 20 minutes. Can you maybe speak to what evidence has led to that change?
Well, yes, the question, of course, is not the definition of the KT boundary, which is that little thin layer which is beautifully documented by the microscopic creatures above and below, and that is effectively instantaneous. The question is the big creatures like dinosaurs, for which there are many, many fewer fossils. There are more fossils of these foraminifera in a thimbleful than the whole Earth's fossil collection of dinosaurs. You know, something like 35 T-Rexes in the whole world, and they're spread over a depth in time of 50 or 100 million years. So you cannot easily tell when the last dinosaur lived. And the same thing's true for a lot of other creatures. So if you want to see whether the extinction was instantaneous or not, you have to do some careful statistics, which is what paleontologists have been doing in the last 10 or 15 years. Collecting more samples, trying to very carefully date or position the ones they see, and then apply some moderately sophisticated statistical tests to see if they're consistent with instantaneous death or a gradual decline. And in the case of the dinosaurs and the other creatures at the KT, they essentially all come out as consistent with instantaneous.
Thank you.
Well, all through this lecture, you were talking about how the asteroids sometimes hit the Earth, of course. And, well, isn't it possible that the Earth might sometimes hit the asteroid?
Right.
I'm just saying.
It's absolutely possible. In fact, there's no difference. The two hit each other. But we only try to deflect the asteroid. It is 1 billion times easier to move the asteroid away from the Earth than to move the Earth away from the asteroid. But you're absolutely right. It's the two hitting each other, and the energy is of their mutual collision.
Hello. I have 2 questions, so I'll start with one. Would it be possible to, because you said the asteroids that would be being deflected are considerably smaller than Earth, about 15 kilometers long, to merely kind of break them up and make it so that there were many more smaller asteroids closer to the Hiroshima impact than there was one large one?
Mm-hmm. Yes, and whether that is a good idea or not depends entirely on when you do it. If you do it like they did in the movie Deep Impact, at the last minute, 2 days or 1 day before the impact, all the fragments will still hit you and you haven't helped at all. It's the same amount of energy. It's like going from a cannonball to a buckshot, and it still would do the damage. If you can disperse it millions of miles away on some previous orbit and break it apart and have the pieces move away, so that maybe only 1 or 2 of the pieces hit you, then that would be a perfectly good thing to do.
Okay, and my second question was, where you say there was no impact shock wave in space, if you had some kind of high explosive strapped to the asteroid, or possibly a satellite that kind of dug into the asteroid and implanted that, wouldn't the shock wave carry through the asteroid in that sense?
It sure would, but any of you who are taking physics courses know that what we're really trying to change here is momentum. And we've got to take the energy of this explosion and translate it into a momentum change. And the way you do that is with Newton's third law. If you want the asteroid to go this way, you have to take a piece of it and push it that way. And so it's not just a shock wave. If the shock wave then produces a crater and material is excavated from the asteroid that goes in one direction, the asteroid will go in the other. And so when you talk about using nuclear explosives, that's what some people think we should do, is explode one right at the surface and basically make a big crater.
Okay.
But then
Thank
who can
you.
say it won't break it apart? We don't know much about how to do that. And much more attractive in many ways are non-nuclear responses where we do understand a little better what's happening.
Thank you.
As luck would have it, I've been reading a book called After the Dinosaurs, which covers the age of mammals. And the author is not exactly supportive of the giant impact theory per se. You know, he agrees with the KT boundary, but he said there are other iridium layers and there are other craters that have happened since the demise of the dinosaur. In fact, one I think was around 37 million years ago and made a 100-kilometer crater.
The Chesapeake Bay crater, probably. Yeah, there certainly have been other impacts since, but none of them is nearly as big as the KT one. The KT crater is 200 kilometers across, and that means it's about 10 times more energy than a 100-kilometer crater. So I guess there probably is some real threshold for catastrophe, where a small one could certainly wipe out even a continent, but it doesn't produce a global effect. And you've got some threshold there that the KT clearly crossed. I worry more about the earlier mass extinctions. I showed you that plot that had 5 big ones. And what is very troubling is that we have not been able to answer yes or no whether any of the others was due to an impact. I really am disappointed. I thought 15 years ago when the KT had worked out and here we understood the celestial cause of this catastrophe, that might be true for the whole history of Earth. And it still might be, but the evidence just isn't there.
Dr. Morrison, thank you for being here tonight. A quick question, since we haven't sent nuclear warheads to asteroids except in the movies, have we done supercomputer simulations of what would result in space if we hit one with the nuclear warhead?
Well, I don't know much about nuclear explosives. I would guess some people have done calculations. But there depends on whether you want to make a crater or you want to heat the surface and then have the surface vaporize. Some way you have to get a reaction force onto it. Or you just have to hit it with such a big bomb relative to the size of the object that you break it apart. As I say, this may end up being even the approach of choice. But for small asteroids, you don't even need a nuclear bomb. All you have to do is hit it with a spacecraft. Just plow a 5-ton spacecraft into it at 10 kilometers a second, and you can significantly change its orbit. So you have to look at each individual case. The big question, which I hope I emphasize and I'll say again, is how much effort should we make now to start developing those technologies? Or should we just say, no, let's wait until we find an object with our name on it?
Thank you.
Could you say how much your budget compares with the budget for SETI, the Search for Extraterrestrial Intelligence?
They're the same order of magnitude. We get $4 million a year from NASA, plus a little in-kind help from the U.S. Air Force to do this survey. And I guess, that would pay for what, 20 minutes of Iraq? Let's say that neither searching for dangerous asteroids nor SETI is exactly accepted in the mainstream of astronomy. They work a little differently. But fortunately, both of them have substantial public interest and support.
I was wondering if there could be one like tomorrow, if one that nobody found. Is that possible?
Say that again. I'm sorry.
I was wondering if there could be an impact tomorrow from an unknown asteroid.
We could certainly have we could have an impact before you leave this room. We would have no warning. There's nobody out there looking. And none of these surveys even wants to try to detect an object at the last minute, because we couldn't do anything about it. If we're going to predict, let's predict them decades in advance and do something. So when you go outside the door, look up.
Dr. Morrison, in your opinion, did the Shoemaker-Levy comet collision with Jupiter bring an end to the argument that evolution on this planet only occurred slowly over time with no catastrophic events?
Shoemaker-Levy 9 comet, which crashed into Jupiter in 1994, certainly helped. And by the way, you may note that both the movies Deep Impact and Armageddon and the official start of the Spaceguard Survey in 1998 both followed just a couple years after that publicly viewed impact on Jupiter. But you're never going to convince everybody. I will say that impact, Shoemaker-Levy 9 impact into Jupiter, was wonderful. It was, those of us who'd been studying impacts never dreamed we'd get to see it happen. And we were so glad it happened to a different planet from ours.
Hi. I was just wondering, what do you think the cause of the Permian extinction is, and what evidence is there?
I wish I knew. If you know what caused the Permian Triassic, let me know, because that was the biggest mass extinction. That was the thing that came closest to the edge of really wiping out much of life on Earth. And there is some evidence for an impact. There's not much iridium, but there are other trace elements like interstellar helium that could have been come in on an impactor. There's no crater, but then the Earth reworks itself so much that if it landed in the ocean, you wouldn't expect to find any crater 250 million years later. And it is a big problem and a very active area of research. I don't know what happened.
Thanks.
Part of me would like to think it was an impact, but that's prejudice more than based on fact.
Yes, I'd like to. I was interested that you had mentioned that the NORAD had picked up quite a lot of supposed impacts in the high atmosphere of the Earth, and that they were frequent, and that was kind of confirming the impact rate that you had worked out for size. But I was wondering as well, the Moon would be a particularly good detector as well, right? It's got a fairly large surface area in the right direction. Is there any value in using observations, perhaps satellite observations of the Moon, to detect the rate of impactors and indeed what type of impacts they actually are?
Well, the Moon and the Earth live together. If we want to look at impact rates on Earth, then these surveillance satellites are very good at it. The thing about the Moon is it really is a lot smaller. The cross-section of the Moon is about 1/20th the cross-section of the Earth. So if we talk about something like the KT impactor on Earth once every 100 million years, it's going to be once every 2 billion years on the Moon. And we're very unlikely to actually see anything happen on the Moon. Although they did, the Apollo seismometers that were placed on the Moon by the Apollo astronauts did detect minor moonquakes when meteors hit. But the Moon doesn't really affect us much. We're unlikely to see a big impact, and if we did, it wouldn't do us any harm here. But the Moon also isn't big enough to shield us from much of anything.
Thank you.
Okay, I have a question about the KT impact and also the Permian Triassic impact and huge lava flows about the same time. I've heard that there's the million square miles of Deccan lava traps in India are approximately the same age as the KT impact in Yucatan and the opposite side of the Earth. And I've heard some speculation that there might be a cause and effect. Or is that taken seriously, or is it considered just a coincidence? And then also related is the even bigger Siberian lava flows that are about the same time as the
That's right.
Permian-Triassic boundary.
The problem with both of those, I mean, it does seem amazing that there should be such a coincidence. The problem is that in both the Siberian case and the Deccan traps in India, the volcanic eruption started between 1 and 2 million years before the extinction and the impact in the case of the KT. So the KT impact didn't start the volcanoes. They've been going for some time. I have a hard time thinking that a volcanic eruption series, no matter how big, that was extended over millions of years, would produce a catastrophe in this sort of sudden sense. It'd be very unpleasant for the creatures living in India or Siberia, but it doesn't fit my mental image of a sudden catastrophic mass extinction. But it's certainly an open issue.
Well, could the Siberian lava traps at some point have triggered a turnover in the ocean so that methane clathrate suddenly melted and released huge amounts of greenhouse gases? And
Maybe. Of course, this is always an interesting question as to whether a much larger greenhouse effect would prove a mass extinction, and maybe we'll find out.